today I'm going to be doing a matched pairs t-test. Now, I'm actually going to take this problem from page 577 from your book, is where it started. It's titled, Is Caffeine Dependence Real? And basically what they did, just to set this up for you, it's at the bottom here, right there, but you can kind of see it, but they have 11 volunteers who were diagnosed as being caffeine dependent. They were barred from coffee, colas, and other substances, and during one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took the placebo capsules, and the order in which they took these were randomized. At the end of each 2-day period, a test for depression was given to the 11 subjects, and they want to know whether being deprived of caffeine would lead to an increase in depression. So, when you look at the data, matched pairs is always going to be a mean because matched pairs is always going to be entered into your calculator. So I'm going to enter this data, I'm on page 578 now, into L1 and L2. Enter, let's clear that out. So if you want me to read it to you, I can do so. 5, 5, 4, 3, 8, 5, 0, 0, 2, 11, and 1. Okay. The next list, L2, is 16, 23, 5, 7, 14, 24, 6, 3, 15, 12, and 0. Now, what's really, really important here is that it looks like you have two separate samples. And eventually there will be a time where these two lists will be two different samples. But right now, this is, when I look at a line, and even the very first person, the 5 and the 16, that is one person, where the first one was where they took, the caffeine, and the second one was where they took the placebo. So these two things, let me find my pen, are, these two are the same person. So it's actually not a two, you don't want to keep these separate because this is what we call a matched pairs, where each person was given the same, both of the treatments. And so what's beautiful about matched pairs, and you'll see as we get into two samples, you really got to be thinking about the differences, is we can calculate, we've actually taken one sample, so we can turn this into one list where we do a subtraction. So I'm going to highlight L3, and I'm going to do L2 minus L1. I like to have primarily positive numbers, and it kind of looks like L2 is larger most of the time. So you might get a couple negative numbers, not a big deal. You could even subtract L2 minus L1. That would be fine too. You would just have to watch how you're setting up your null and alternative hypothesis. So now I'm going to continue with how we would set this up. So biggest thing right now is L3. At this point in time, I can even delete L1 and L2 because you are not using it whatsoever. If this is a matched pairs, if that person at 11 is the same person at 12, all I care about is the difference in the improvement in the depression score of that one person. So I only care about L3. That's the beauty of matched pairs is it looks like two samples, which requires quite a bit more work. There's actually only one sample. So let me get this guy going. So with that set up, the question that we are trying to find in this, let's see here, what are they looking for? They want to know whether being deprived of caffeine would lead to an increase in depression. So that's their depression of each of them. So our null hypothesis, HO for this, let me get this guy for you guys. We'll put this right here. Our null hypothesis, HO, is actually about, and this is weird, it's the mu of the differences. You're going to see me mu differences. So the assumption is that there's no difference between the caffeine pill and the placebo. So the assumption is that your difference is 0. Now the alternative is that there is increased depression with the placebo. So if that's the case, so the placebo would give you more depression because you don't have your caffeine. So we're trying to show that there's more depression with the placebo. So in this situation, sorry, I shouldn't have written equals. We're going to write the mu of the differences is greater than 0. Okay, and that in this situation, remember the way that we are subtracting, and maybe I'll write this up here, is our differences are the the way I did it, placebo minus the caffeine. This is actually EI. NE. Okay. Placebo minus caffeine. Anyways, let us define our population parameter. So the mu of the differences is the true population mean difference in depression scores, and then this is where I might, just kind of put placebo minus caffeine, just so you know, and they know, the graders know which way you were subtracting. So I've got my null hypothesis, and now the other variables with means are going to be your x bar of the differences, your s of the differences, and your n of the differences. So when I go back here, and I got to go grab my mean, my standard deviation, I'm going to go stat, calc, one variable statistics. But it's not, it's all about the differences in a matched pair. So we're going to be doing L3. Okay, and our x bar turns out to be 7.36, and our standard deviation is, remember, choose the S. Whenever you're given a choice, 6.9, I don't know, 6.9 if we want to just use that. Okay, so here we are. 7.36. Standard deviation is 6.92. 6.92. And N is 11, so 11 observations there. So we will now write our conditions. Conditions for a matched pairs t-test. I need to turn the light on. With n minus 1 equals 10 degrees of freedom. If you don't know sigma, which is most likely n means, you are on a t-test, and you have to worry about your degrees of freedom. So number 1. Okay, now normally you've done this so many times, you're ready to go. Simple random sample from the population. Problem here is that this is not a simple random sample. If you read it, it is actually just a bunch of volunteers. And they're not just sampling, they're actually doing an experiment. So I'm going to change this up on you. You have to adjust and be on the lookout for this. When I used to teach this, and years ago, I always just wrote simple random sample, but you kind of start to pick up on things. And, if you're not sampling here, you have, there's something else that's got to be going on. So here's what's going to happen. We are going to say that they are performing, it's not a random sample, but it is, the data come from two groups in a randomized experiment. It's not two groups. Sorry, let me change this to, let's write researchers randomly assigned treatment order. Okay, state that it's a randomized experiment. In fact, if I could rewind this video for a second here, I would write this first, randomized experiment, and then state how it was. Researchers are randomly assigning the treatment order. Who's getting which pill at, in what order. So remember, we're not sampling, but it's a randomized experiment, and that's where the random, the random condition is going to be met. Now, number two, which you guys, again, should be just doing so fast and not really thinking about it, is a population greater than 10N. Well, the reason we check that condition is if you're sampling without replacement. Well, we're not sampling at all. It's an experiment. So in this situation, what we need to do is we have to look at the independence and see within the experiment, how are we aware of, if these people in the experiment are independent of each other. So we don't have to check population greater than 10N, and then we're just going to have to assume that the changes in depression scored for one individual, what doesn't affect the next. So we will assume the changes in depression for one individual does not affect the changes for another. Now, in real time that I'm actually creating this video, this was in binomial. Remember when we did population greater than 10N, you had two choices. Well, this is the other choice. If population isn't greater than 10N because you're not worrying about sampling, you just have to say that the results of one person is not going to affect the results of another. So these two conditions are going to come together and show that you have independent subjects. Okay, now the third condition. Okay, so they were all a thinker for this one, but the third condition always, if I'm on a mean, which again you are, let me show this again. Let me get a larger one. I don't know where it is. So hopefully you can see that. Let me zoom in for a second for you. Okay, we go through the conditions again. We hope n is greater than 30. It's not. Is n between 15 and 30? No. Well, okay, we're here at n is less than 15. So that's the one we're going to use. So I'm going to say, zoom out again. N is less than 15. Having trouble writing here. Where n is equal to 11. So we got to take a look at a box plot. And it's got to be the box plot of the differences. So go back to your plots, and I'm already set up for L1 with, oh no, I want to be in L3, the differences. Okay, so make sure you're there, because that's the only list you care about. I'm going to go to Zoom 9, and again I see, very slight skewness. I'm okay. am going to be okay to proceed here. And there's no outliers, so it looks like we're okay to go without any strong skewness. Very slight, and I would just proceed here. Nothing to be too crazy about. So copy down your box plot. And make a comment on it. Box plot shows very slight skew with no outliers. Okay to proceed. Or I'm going to proceed. Maybe a little bit of caution there with some the skewness, but really not bad, because t-distributions are robust. So this third condition will tell you that a t approximation is okay to proceed with. Make sure you write that. Point here, a lot of people forget that. So now we've got our curve. It's a sloppy video. So here I am. There's my curve. 0 is going to go in the middle. That's the null hypothesis, always, always, always. The sample was 7.36. That was the differences in the sample. And there we go. So here we are, people. Formula. Test statistics. T is equal to, page 5 of your Lime sheet. Statistic. X bar minus the parameter, Greek letter mu of the differences, over the standard deviation of the statistic. Well, we don't have sigma, so instead of using sigma over square root of n for means, I'm going to use S over square root of n. Formula substitution. 7.36 minus 0 divided by 6.92 over square root of 11 is equal to. Oh, I forgot, what I usually do, and to be honest, I don't know. You've already stated in the title, but I usually add a fourth condition here for matched pairs where I just say the data is matched. Or say something about paired data, as sometimes you'll see that. Okay, people. We go to our test menu. It's going to be very similar to what we did with just a regular one sample mean test. Stat test. It's a mean, so don't use the word proportion. It is one sample. It looks like two samples at first, but you don't treat it as such. It is just one sample in L3. T-test. My data is here with L3. My null hypothesis is 0. And I am doing a greater than, so that's like right here, greater, and I'm going to hit calculate. So T is equal to 3.53, and your p-value is equal to 0.002. 7, I guess we'll say. Okay, so it looks like we are in a PLAR scenario. P is less than alpha, so Plartis. And we will write, since the p-value is less than alpha equals 0.05, we reject HO, PLAR. There is sufficient evidence. There is sufficient evidence to conclude that, and let me look back at the sentence again. they want to know whether being deprived of caffeine would lead to an increase in depression. So there is sufficient evidence to conclude that being deprived of caffeine would lead to an increase in depression. And there you have it. A matched pairs t-test. It becomes a one sample. It's very nice. What you want to be on the lookout for is when I do a two sample mean and I'm entering data into my calculator, you don't use L3 if they're two separate samples. The reason I use L3 here is because it was one person who was measuring their placebo depression score and their caffeine depression score. So be on the lookout for that when we do a two sample mean significance test. Okay guys, have a wonderful day.